Hello everyone and welcome to my YouTube channel. Today I'm going to introduce you the topic of fingerprint recognition, a fascinating area within pattern recognition and biometrics. Somewhere on the tip of your finger there is a pattern so unique that no two people on earth share it, not even identical twins. For centuries, humans have used this fact to identify criminals, authenticate identities, and solve crimes. But how does a machine read it? How does an algorithm look at a smear of skin and say, yes, this person? That is what we are going to understand today, completely from first principle. A fingerprint is the topographic impression of the epidermis, the outer layer of skin on your fingertip. It consists of alternating ridges and valleys formed through a combination of genetic instruction and random environmental events during fetal development. Because even genetically identical twins experience different physical conditions in the womb, different position, different fluid pressure, their ray pattern diverge. The modern scientific era began in 1686 with Marcello Mablinghi's anatomical descriptions of rib structures. By 1888, Sir Francis Galton has introduced what we now call Minutiae, the tiny local discontinuities in rich structure that anchor modern matching. By 1924, the FBI has a database on over 800,000 fingerprint cards. By the 1960s, manual matching has become impossible at that scale. That is when the age of RFIS began, and now we have so many brilliant fingerprint biometric systems. Before any algorithm can run, the fingerprint must be digitized. Today, most systems use large-scale sensors where the finger is pressed directly against an electronic surface. The most common technology is FTIR, frustrated total internal reflection, which is absorb light, volleys reflected, a lens captures the result onto a digital sensor. Two other families exist: solid-state sensors using silicon pixel arrays and ultrasound sensors using echo-based imaging. When we look at a fingerprint globally, certain regions show distinctive shapes called singularities, loops, deltas, and words. The core point at the center of the northernmost loop is used by many algorithms as a reference for alignment. At the local level, the most important features are Minutiae, points where the ray structure is discontinuous. A termination is where a ridge ends. A bifurcation is where one ridge splits into two. Its minutiae is encoded a triplet x, y, and angle theta. Extracting minutiae from a raw fingerprint image is a multi-step highlight. First, we compute two maps from the image: the local orientation field, the angle that ridges run at its pixel, and the local frequency map, how densely packed the ridges are. These are then used to isolate the fingerprint foreground from the background through segmentation, and to design adaptive contextual filters tuned to the local ridge structure. These filters enhance the image, sharpening ridges, reducing noise. The enhanced image is then binarized into black and white, and things so very rich is exactly 1 pixel wide. Finally, after scanning for minutiae and applying a filtering pass to remove superior detection, and we have our final minutiae set, the fingerprint reduced to its mathematical essence. The crossing number is an elegant local operator. For each pixel in the thin binary image, we look at its 8 immediate neighbors arranged in a ring. The crossing number is half of the sum of the absolute differences between consecutive neighbors as we travel the ring. A value of 1 means the ridge ends here, a termination. A value of 2 means the ridge continues, just a normal ridge pixel. A value of 3 or more means the ridge branches, a bifurcation. Here is the fundamental challenge of fingerprint matching. Two impressions of the same finger can look dramatically different due to rotation, displacement, nonlinear skin distortion, variations in pressure or image quality. Meanwhile, two different fingers can sometimes be deceptively similar. The matching algorithm must maximize the similarity score between genuine pairs while keeping the score low for imposter. Three families of matching algorithms already challenge correlation-based, Minutiae-based, and rich feature-based. The simplest approach is correlation-based matching. We take the template fingerprint T and the input I, and search for the rotation and translation that maximizes their cross-correlation. Mathematically, the similarity score S is the maximum cross-correlation over all possible shifts and rotation. But this approach faces a serious problem. Nonlinear skin distortion means no rigid transformation can perfectly align two impressions of the same finger. The most widely used approach in Minutiae-based matching. The fingerprint is reduced to a set of Minutiae points defined by a position and angle. To allow the template and the input sets, we use the Hough Transform. For every pair of Minutiae, we compute the required translation and rotation, then cast a vote in a 3D parameter space. The transformation within the highest vote count becomes our best alignment hypothesis. We apply this transformation and count how many minutiae overlap within an acceptable tolerance. The scale is then divided by the maximum number of minutiae between the template and the input to yield the final match score. A third approach is rate feature matching. The fingerprint is divided into concentric sectors around the core point. Each sector is processed through orientation-sensitive filters, and the responses are assembled into a feature vector called the FingerCode. To match two fingerprints, we compute the Euclidean distance between their FingerCode vectors. So, how do we know how well this system performs? Since the early 2000s, a series of international competitions called the Fingerprint Verification Competitions, or FVC, have provided standardized benchmarks. Participation grew from just 11 algorithms in FVC 2000 to 70 algorithms by FVC 2006. The best system achieved an equal error rate, the point where 4 accepts and 4 rejects are equal, of just 2.07%. Yes, three major urban challenges remain. First, security against fake fingers and template reconstruction. Second, quality degradation from wet, dry, scar, or worn ridges. Third, scalability, searching billions of records quickly and accurately. To arrest these, research continues in through detection, robust feature extraction, and multimodal fusion. What began as ink on paper is now a sophisticated cascade of algorithms. To a computer, a fingerprint is no longer just a picture of riches and valleys, it is a highly structured mathematical object. It is an orientation field that guides the flow, a set of singular points that define the global pattern, precise coordinates of minutiae, discontinuities, and a holistic fingercode texture vector. The system built around the representations now authenticate billions of people every day. And yes, the problem remains alive, still yielding ground to research, one algorithm at a time. Thank you so much for watching. If you found this video helpful, please don't forget to like, share, and subscribe to my channel.